So dear students, so far we have familiarized ourselves with the concept of thermodynamic potentials, and we have discussed two of the important thermodynamic potentials, namely the internal energy and the enthalpy. So before we discuss about the third thermodynamic potential, namely the Helmholtz function, let me give a quick recap about what we have learned so far. So we defined a thermodynamic potential as a function, a state function of thermodynamic variables such as pressure, volume, temperature, entropy, etc., which together with the first law of thermodynamics and the definition of change in entropy in a reversible process will help us to study the equilibrium properties of any system under specific conditions or constraints. So in that line, we have defined U as the introductory thermodynamic potential. U was defined in terms of the change in internal energy. UF minus UI was found to be equal to work done under adiabatic conditions. So that is the definition for the existence of the state function U. And we have seen that whenever you are able to express the internal energy of a system in terms of the volume of the system and the entropy of the system, we elevate this function to that of a potential function. That is, whenever you are expressing the internal energy of a system in terms of its volume and entropy, lot many information can be obtained from this function under specific conditions. So we called internal energy as a thermodynamic potential. And this V and S are actually called the natural variables for the internal energy function. So as I already mentioned in previous video, U can be expressed in terms of other variables as well, but the U will be having the status of a potential function if and only if you are able to express U as a function of its own natural variables. So remember that volume and entropy are natural variables for the internal energy function. And we have seen that this internal energy function U will be achieving its minimum value under the equilibrium state of the system for a isochoric isentropic process. And the differential change in U can be expressed as du. What is du equal to? Du was defined in terms of the first law of thermodynamics. We have defined du as TdS minus PdV minus PdV. And using this equation, you are able to find out a differential relationship for temperature as well as pressure. This is what we have done with the internal energy function. So thereafter we defined another thermodynamic potential, namely the enthalpy. So the enthalpy, which was represented by H, is defined. H is defined as U plus PV. Mathematically, it is defined as U plus PV, where U is the already defined internal energy function and pressure and volume are also finding a place in the equation. So H equal to U plus PV. So this is a mathematical definition for the enthalpy. And how do we get this relationship? So as I mentioned, the new thermodynamic potentials which are equivalent functions, which are all equivalent functions, can be obtained from another thermodynamic potential by the method of Legendre transformation. So the Legendre transformation technique in mathematics helps us to define or obtain new thermodynamical functions which are acting as potentials from the already existing or already defined thermodynamic potentials by suitable basis change. I will be explaining the Legendre transformation technique in detail in a separate video. So we can say mathematically you obtained H by transforming U. So U, which we expressed as a function of V and S, can be transformed mathematically by Legendre transformation into H, and we will see that the natural variables of H will be P and S. The natural variables of H will be P and S instead of V and S. So you can see that that's the only difference here. The volume the role of volume has been replaced by pressure, and the entropy is a common variable in both internal energy function as well as what enthalpy function. So that is one thing you have to remember. And see, from this definition of H, you will be able to write the expression for the differential change in H, dH. And what was dH equal to? We could write dH is equal to see for final expression was just 1 minute. TdS, so TdS, that is same equation, sorry, TdS plus VdP, TdS plus VdP. So that was the expression for dH. And as we have discussed for internal energy function, the enthalpy function will be attaining a constant value, or dH will be equal to 0 when the process is isentropic, that is S equal to constant and P equal to constant. Moreover, when this H is a minimum, H has attained its minimum value under constant entropy and constant pressure, then we can conclude that the system would have attained its equilibrium. So the equilibrium state of the system is characterized by the minimum value of its enthalpy under isentropic isobaric process. So that is something to be taken care of, right? So the general conclusion is that in every process, depending on the nature of the process, one or another thermodynamic potential of interest will be attaining its minimum value when the system has attained a state of equilibrium. And that is one reason why we have given the status of a potential function to all these different quantities, because as I mentioned earlier, I would like to repeat it. The concept of a potential function has been borrowed from mechanics, from the idea of potential energy or potential, whether it is gravitational potential or electric potential in electrodynamics. So whenever the mechanical system is attaining its maximum stability or equilibrium condition, the potential energy V would have become its minimum value. So from this motivation, from this analogy, the potential functions are defined in thermodynamics. So that is a common criteria that you remember. Now it's time that we come back to the new thermodynamic potential that we are going to define, namely the Helmholtz function. So the Helmholtz function is usually represented by capital letter A, or some others prefer to use capital letter F, where this F denotes some kind of free energy. Now, like we defined the enthalpy from the internal energy function, we will be able to define Helmholtz function also from, or also in terms of the internal energy function. So that is what you have to remember. The internal energy function is already defined. So from internal energy function, you can define two new thermodynamic potentials. One is the enthalpy and another one is the Helmholtz free energy. So two new thermodynamic potentials can be defined from the already defined or well-known familiar potential, namely the internal energy. So how do we define it? I told you the technique is the Legendre transformation. So you perform one kind of Legendre transformation, you get H, and you perform another type of Legendre transformation or another Legendre transformation, you will be getting the Helmholtz free energy. So let's see the definition. So this is the defining equation as far as Helmholtz free energy is concerned. A equal to U minus Ts, where the symbols have got its own meaning. So T is the temperature and S is the entropy of the system. And I can conclude, or I can say that the Helmholtz free energy that is obtained from U, you can see that U is there. So I can say U, which is what are the natural variables of U? We have seen that V and S were identified as the natural variables. So I am writing U, V, comma, S. U expressed in terms of the volume and entropy of the system. That's only meaning. So it can be transformed. It can be transformed into A, new thermodynamic potential, where the natural variables of A will be volume and temperature. So I just suggest you that you memorize the natural variables of each of the four thermodynamic potentials that we are going to see or we have already discussed. So that will be helping you to take forth our discussion further very easily. And don't worry, I will give you some mnemonic technique, some ordinary techniques to memorize all these things towards the summary part of our this topic. Okay, so this is yet another Legendre transformation. So just have a look at this equation. That's what I suggest you always. So here you can see the natural variables are V and S, and here the natural variables are V and T. So you can see that V has been retained as the common variable in both U and A. And what is the only change? The S in U has been replaced with the T in A. So S is replaced with the T in A. So you get a new function. And that is actually the technique of Legendre transformation. Okay, you will be changing the basis of the functions by the mathematical technique. So now, just so we already got the definition. So this is the defining equation, and this is the mathematical technique behind obtaining this equation. Right? Now, let's see why we are so bothered about defining a new thermodynamic function when already you have two with you. You have U and H. Okay, why are we not satisfied even after having two such functions? The reason is that this thermodynamic potential A is specially important. It is specially important because it will help us to link the macroscopic theory of thermodynamics with its microscopic counterpart, namely the statistical physics or statistical mechanics. So in the beginning of our thermal physics course, I had told you that there are several branches of thermodynamics. Thermodynamics can be considered as the mother branch. Okay, and there are different topics like kinetic theory is there, there is statistical mechanics, and statistical mechanics is an advanced branch of what? Thermal physics actually. So you can see that the link between, or I can say the bridge between, the connection between thermodynamics, which is an empirical subject, and statistical mechanics, which is rather probabilistic interpretation of the subject, can be achieved if you are able to define a new function like Helmholtz function. And you will see that whenever you learn statistical mechanics as a separate course in your post-graduation in MSc classes, you will understand that throughout your discussion of statistical mechanics, you will be relying on the Helmholtz function in order to obtain information regarding the system that we are going to discuss. Okay, so always remember that this Helmholtz function is so important, okay, in the study of a thermodynamic system, especially when you are treating the system by using the technique of statistical mechanics or probability approach, right? So that is why, okay, it's so important, right? Now a word I should add, because you know that thermodynamics is giving the definition of entropy. Thermodynamics introduces the concept of entropy as a state function. But even after discussing so much about entropy in our previous sessions, I know that there is some sort of an abstractness. Okay, maybe in a varying degrees depending on people. Okay, different person to person. Certainly, there is some sort of an abstractness that is associated with the concept of entropy as we defined in thermodynamics. And one of the limitation of thermodynamics is that we could not define the absolute value of entropy, right? Absolute value of entropy of a system at a finite temperatures. Instead, we always defined what is known as change in entropy, ds or delta s. ds or delta s was defined by thermodynamics so far. Okay, and it was statistical physics which could define the absolute value of entropy of the system by the famous Boltzmann equation that we have already stated. So that is yet another improvement of statistical mechanics. So you can see that we are able to go from this thermodynamics which was a bit abstract. Okay, it was empirical and we couldn't get a complete idea about certain quantities like entropy and all. But see, by using the concept of Helmholtz free energy, we are able to establish all these facts, okay, successfully. So that is why we discuss about Helmholtz function. Right now, as I mentioned in the introductory session on thermodynamic potential, the Helmholtz function, mathematically it's a function. Hence we call it as Helmholtz function. It's a function of natural variables v and t, is better known as Helmholtz free energy. It's better known as the Helmholtz free energy. Okay, so please have your attention on the word free energy. Free energy, and why it's known as the free energy, we will try to understand, okay, by the end of this particular lecture, right? So now these are the preliminaries as far as the function is concerned. So the thing is that it's a useful thermodynamic potential like U and H. That's what. Now see, let's do some ordinary algebra as we have done with U and H, which will give you more insight into the relevance of A, right? So we have automatically we have, see, this A, right? A was defined as U minus Ts. So A equal to U minus Ts. That is the equation we have. Now, as usual, let's take the differential of A. I'm taking the total differential of A. what is the meaning of taking the total differential of a quantity? Why we are taking? Mathematically we tell that take the total differential of A. I have already mentioned it in some module number 1 or 2. What is why do we take the total differential of A? Or what is the physical meaning of taking total differential of a quantity in thermodynamics or elsewhere in physics? See, we take the total differential of A whenever we are interested in the infinitesimal changes happening to a function. See, for example, suppose you have a function x and it is related to some other variable, say y, x is equal to a y plus b or something else like. Now if you want to know what will happen to this function, x due to a very small change, or what happens when a very small change happens to x. So you know, very small changes happens when the process is what? Infinitesimal process. So in order to understand the effect of an infinitesimal process happening for a system, we take the total differential of the corresponding function. So let me write that for an infinitesimal process, so you should be able to convert the physical concept with the corresponding mathematical technique. For an infinitesimal process, what should you do? You should take, if the process is infinitesimal, you should take the smallest change, the infinitesimal change in the quantity. So I'm taking dA. Mathematically, I'm taking the total differential of A. That's all. So what will be dA equal to? As usual, you have to take the total differential on the right side quantity. So it will be equal to simply du. You know the technique, du minus, so TdS minus SDT. TdS minus SDT. Okay, yeah, you're familiar, I think. So it's equal to, how do we modify again? Now from the, see, just recall always what was the definition of the thermodynamic potential. Thermodynamic potentials are such state variables of pressure, volume, temperature and entropy, which together with the first law of thermodynamics and the definition of entropy change for a reversible process will be able to define new functions and will be able to help what? Will be able to explain the equilibrium behavior of systems. So we are tempted to use the first law of thermodynamics. And what's the first law of thermodynamics? So it says that du equal to, in several ways you write, du is equal to d bar q, is not d bar q minus pdv. Okay, du equal to d bar q minus pdv. This is the equation that we have already used, right? It was d bar q plus d bar w, and d bar w was replaced with minus pdv, right? Now so du minus tds. So let me write du in terms of d bar q. So it's equal to d bar q minus pdv, okay, minus tds minus sdt. Now what we will do? You will use the second equation. So this is one equation that we have used, and we'll be using the second equation. What is the second equation? That is the definition of change in entropy for a reversible process. We consider all these processes to be happening reversibly. That's an ideal assumption behind, untold assumption behind all our derivations. We are dealing only with reversible processes unless it is specified that we are dealing with irreversible processes, right? So ds was defined as d bar q over t, right? So d bar q can be always replaced as tds, as we had done previously also. So this d bar q, this is nothing but tds, and this is minus tds. They mutually get cancelled away, and what we are left with? We are left with the minus pdv minus sdt, minus pdv minus sdt, and this is an equation that's worth remembering or noting. And why this equation assumes importance? So let me call this one as equation number 1 so that I can make references if needed, and let me call this equation as equation number 2. Why this equation assumes relevance? Because this equation gives you an indication regarding the functional behavior of A. So I can say this A is a function of two variables. What are the two variables here? So one variable, how do you identify variable in an equation? Because that variable will be expressed as change, dv. dv means change in v, means v is a variable. And the other variable here is t, because it is written as dt. dt means change in t, means t is also a variable. So I can say the variables of, or better, natural variables of the function A are v and t. V and T. So A is a function of V and T when it assumes the status of a thermodynamic potential. Right? So let me say that this is my third conclusion, and you can see that this is this equation what I have already used here. This is this particular conclusion that I already have introduced, so that it is pedagogically easier for me to tell you what I'm doing, what I'm going to do. So A is a function of V and T. So V and T are the natural variables of Helmholtz free energy. Okay, that is also what you have to keep in mind. It's okay. Now that is there. Once again, actually you can talk volumes and volumes about each of the functions, but we will restrict ourselves for the minimum requirement that we are doing, and I think I will do a separate session for further properties of each of these functions. Okay, so what I'm discussing in this session is the barest minimum that every student should be able to take home, right? So now once more, next thing, so let me take a special case. Let me take a special case. See, I'm taking a from equation number 2, I'm taking a very special case. See, think of what about dA when V and T are constant. So if V equal to constant, don't get confused with my V and the U. It almost looks same. I want to write it better, but I'm not able to write it by using my digital pen. Sorry. So if V equal to constant and simultaneously if T equal to constant. So means two constraints. I told you constraint means some limitations we are putting on the system. If V and T both are maintained as constant, then you know equation number 2 will predict that dA will be equal to 0. Equation 2 says that dA equal to 0, right? So dV will be equal to 0 and dt will be equal to 0, so which makes that dA equal to 0. So dA equal to 0 does is not okay. It simply means that the A is a constant. So under this particular condition, the Helmholtz free energy of the system would have attained a constant value. Whenever V equal to constant and T equal to constant for a particular thermodynamical system, you can be sure that the Helmholtz free energy of that particular system would have attained a constant value. It will not change anymore. Okay. Now, one more thing is important, right? See, if let's say once again I can say that a very special case, this one what we discuss is a special case. I'm going for a very special case. What is a very special case? The case is that if the system under our discussion has achieved its thermodynamic equilibrium, if the system under discussion has achieved its thermodynamic equilibrium, right, then you can make sure that you can conclude that this Helmholtz free energy would have reached its minimum value. So this is the most significant concept that you should keep in mind. A would have achieved its minimum possible value. Remember that minimum possible value is also a constant. A would have achieved its minimum possible value when the system is in its equilibrium, system in thermodynamic equilibrium. Remember, I have already used this concept here. Don't you remember that? Whenever H of the system, enthalpy of the system has achieved its minimum value, that also defines what? The equilibrium condition of the system under question. But so don't ever get confused. So H equal to H minimum and A equal to A minimum. No. Okay. So it doesn't occur simultaneously. Remember, you have to use the proper conditions under which this H will be H minimum. H will be equal to H minimum for a system in equilibrium only if S and P are constant. Only if the natural variables, what is the thing? Yes. I think I just made a yes. Okay, what are the natural variables? P and S. So only if its natural variables attains a constant value, then the equilibrium state of that system, that particular system, will be characterized by the minimum value of that particular thermodynamic potential. So here, whenever the natural variables volume and temperature of a thermodynamic system is constant, And if you know that the system is in thermodynamic equilibrium, you can make a alternate conclusion that its Helmholtz free energy would have attained a minimum value. Hope it is clear to you. And that's what I have already just written here, typed here as the conclusion. So for this particular conclusion, for a reversible isothermal T equal to constant, isochoric V equal to constant process, for a reversible isothermal and isochoric process, it should happen simultaneously, not separately. The Helmholtz free energy is a constant in general, and that constant will be the minimum value. It will attain a minimum value when the system has achieved equilibrium condition. So that's the physical relevance, one of the physical relevance of the Helmholtz free energy. Okay, now before I conclude this session on Helmholtz function, let me justify its name, its alternate name, that it is known as Helmholtz free energy. Why the word free? So, to explain that, concept, let me just invite your attention to the definition of Helmholtz free energy once again. So what was our definition of Helmholtz free energy? Mathematically, A is equal to U minus Ts. Just have a look at this equation. Just have a look at this equation, and I suggest you having a look at the equation. Better you stare at the equation. That's always better. You stare at the equation with an intention to understand what is the meaning hidden there. See, so this is A, right, which we have been regarding as Helmholtz function, thermodynamical, it's not potential function. And here U, another thermodynamic potential function, and here there is Ts. So from our basic concept of internal energy, U represents the sum total of the kinetic and potential energies of a system, right? Is it not? It represents some sort of the energy content of the system, right? So U is a representation of the total energy content of the system under certain specific conditions. Of course, that is there. Conditions apply. And A is not equal to U. That's what you have to understand. A is not equal to U. And A will be equal to U when this Ts term is equal to 0. So there is a Ts term. Remember, what is this Ts term? This Ts term will be having the dimension of energy. That's for sure. Okay. I don't remember whether I have, I think I have mentioned it earlier as well. So Ts term will be having the dimension of energy. How? Because the SI unit, let's check it by using units. That's quite easier. S is joule per Kelvin, right? Entropy unit is joule per Kelvin, and T is what? Having unit Kelvin. So you multiply T with S. So K and K will be getting cancelled, and what you are left with is what? Ts will be having the unit as joule, which is nothing but a unit of energy, right? So that is why you are able to subtract the Ts term from U by the principle of homogeneity of dimensions, what you already have learned in your +1 classes in the very first chapter. Okay, you can add and subtract only those quantities which are having same dimensions to make a physically meaningful relationship. So A equal to U minus Ts, right? So you can see that this A represents an energy value that is less than the internal energy of the same system. We are talking about the same system. All these parameters belong to the same system. I have a system with me, and the system has got some value of Helmholtz function, some value of internal energy, some value of temperature, and some value of what? Entropy at a particular state, right? All these functions are state functions. That's the reason. So when the temperature of the system increase, suppose either when the temperature of the system increase or when the entropy of the system increase. So let me talk in terms of the entropy, because already we have concluded from the second law of thermodynamics, the principle of increase of entropy, that all spontaneous process will lead to an increase in the entropy of the system. Okay, so let me say that S will be increasing in all natural processes, or in all spontaneous processes, or in all what I can say irreversible processes. Also, I can say the entropy of the system will be going on increasing. So what will happen as S increases, even if T equal to constant, when S increases, the Ts will be increasing. So as Ts increases, Okay, more the A will be getting decreased further and further. So we can see that as S increases, A will be decreasing, and this is what you have to keep in mind. As the entropy of the system increases, the Helmholtz free energy of that particular system will get what? Decreased in general, because you treat, okay, so if you consider U to be a constant, right? Now what does it mean? In a plain meaning, it just means that, okay, the A can be regarded as the useful energy. A can be regarded as the useful energy. What is mean useful energy? The energy that is actually that can be derived from a system. Means you cannot completely use the internal energy of a system under every condition. So you will be able to, but you will be able to use some part of the internal energy completely. You can convert some part of the internal energy of a system completely into useful work, and that part under special condition is what is known as Helmholtz free energy. And you can see that that is equal to the internal energy minus some energy, and this term, as I told you, representing an energy is usually identified as some sort of a latent energy. Latent, like we have defined latent heat. This one is known as a latent energy. What does mean latent energy? That's a hidden energy, or I can say it's a sleeping energy. Means I cannot make use of it. So every system has got some amount of latent energy. Okay, that is equal to Ts. And as entropy of the system increases due to one reason or the other, the latent energy will be also going on increasing. And that is one reason why. And what will happen to this A? A will be going on decreasing. So I can say the available energy, which is otherwise known as free energy. So the word free here actually means available energy. The word free here means the available energy which can be converted into useful work. Okay, so I just invite your attention to one previously learned concept, the principle of increase of entropy. And the entropy was identified as a measure of unavailability of energy of a system. Hope you remember. Or we concluded that as the entropy of the system increases, available energy in the universe goes on decreasing. I repeat, as the entropy of the system increases, the available energy of the system will be, or of the universe will be going on what? Universe in total or in general will be going on decreasing. And can't you see that? Okay, or don't you remember that at equilibrium, what about the value of entropy for a system? We had concluded earlier that at equilibrium, S would have reached its what? Maximum value. So from this relationship, when S has achieved its maximum value, what would have happened to the corresponding A of the system? Certainly, A should have reached its what? Minimum value. A should have reached its what? Minimum value. Okay, so can't you say that these two things now go together? So that is what we already have defined here. So try to relate it, please. So whenever a system undergoing a reversible isothermal isochoric process has attained its equilibrium, we have concluded from our previous discussion that its Helmholtz free energy would have attained its minimum value. And the minimum value of Helmholtz free energy corresponds to the maximum value of its entropy. And that is what is given by this equation. Right? And hence we conclude that it's always better we consider this function A to be a measure of the available energy that can be usefully converted into work. Right? And hence the name free energy, Helmholtz free energy. Similar to this Helmholtz free energy, as I told you in the introductory session, the next thermodynamic potential we are going to discuss, namely the Gibbs function, also has got the same status. Gibbs function is also better known as Gibbs free energy. That's the more common terminology that is used. Okay, so that is the second physical relevance that I want to tell you. Right? It's considered as a free energy. Now, before we conclude, okay, one more thing. I think I can just conclude by saying you one more thing, that this equation number 2, from this equation number 2, I can define two quantities. P, one is P. Okay, in order to define P, we have done the same thing with H and U also. So I can write P of the system, I can write in terms of A of the system. How to write P? For that I should make this term equal to 0. So to make this term equal to 0, you make T equal to constant. So P equal to dou A dou A with respect to dou V, dou A with respect to dou V at constant temperature. Is it enough? No, it's not enough. One thing is missing. Why? There is a negative sign here. Should not neglect it, because all this negative sign has got some physical meaning. So P of the system is related to the Helmholtz free energy of the system as the derivative, partial derivative of A with respect to V at constant temperature. That is one relation I am going to get. Another thing is that the entropy of the system can be now related. The entropy of the system can be now obtained from its Helmholtz free energy. Okay, so it's a potential function. So potential function means that the function has got the capacity to give you the value of other relevant functions if you do not clearly know that. Okay, so S is equal to, what be S is equal to? That is equal to, once again you take the partial derivative. This time you need to make this dV term 0. So V should be maintained a constant. So S will be equal to dou A with respect to dou T, dou A with respect to dou T, dou A by dou T. What do you have to maintain constant? The constant to be maintained is what V should be kept as a constant. V should be kept as a constant. And one more thing is that there should be a negative sign, and that negative sign is so significant. Okay, please never neglect the signs that we are finally getting in all the thermodynamic relations, because that sign will have something to tell you. Okay, don't neglect it. And for example, okay, let me try to interpret what is the meaning of this negative sign in this equation. So what is the negative sign in this equation? Just look at this equation and can you mention what will be the negative meaning of the negative sign here? From the discussion that we have already done, you can see that the right side, you look at the right side, physical meaning, always give the importance to physical meaning. So what is the right side representing? It's dou A by dou T. What is the meaning? The change in A with respect to change in temperature of the system, keeping volume constant. So change in A with respect to change in temperature, keeping volume constant. And the left side gives you entropy, right? So let me assume that the change is either I can take that, let A is increasing, let A increases. So when A increases, I can say this dA is positive, right? Because dA or dou A, whatever it is, dA is equal to A final minus A initial. That's always there like that. So if A increases, A final will be greater than A initial, or dA will be equal to what? Positive, right? dA can be either positive or negative. So when A increases, this dou A will be positive, right? Now this minus sign, what does it mean? It shows that the entropy, okay, the entropy of the system will be decreasing. The entropy of the system will be decreasing. That's the meaning. That's the physical meaning of that negative sign. And if you think of the reverse, if A certain process happens such that the A of the system decreases, means the system is now tending towards what? An equilibrium. So when the system moves towards more and more towards the equilibrium state, then you can see that the value of the A will be going on decreasing, and finally it will try to attain its what minimum value. That's what we have concluded. So when A decreases, it says that S must what? Increase. So this inverse sort of relationship between A and S of the system under specific condition is actually hidden in this negative sign. So all these negative signs can be interpreted if we are patient enough, right? So that's about the Helmholtz function. Basically there are some more properties of Helmholtz function that I will be doing as a separate session, right? So before we conclude, remember, so far we have discussed 3 of the important thermodynamic potentials, starting from U, then going on to H, and then finally on to A. Each of this each of this thermodynamic potential will be useful under one context or another context. We don't use all the thermodynamic potential in the analysis of a system. Either you will be using U for analysis, or you'll be using what? The H for analysis, or you'll be using A for analysis, depending on the conditions that is available or that is existing with the particular system under question. And the ultimate aim of defining these all functions is to study the properties of the system under equilibrium, or to analyze the equilibrium properties of a system under consideration. Okay, in the next session we will be introducing the remaining important thing, what is not Gibbs free energy or Gibbs function, and finally we will recap all those things. Thank you.